Hello everyone, today I give a presentation about our work appeared in NDSS this year. The title is Hybrid Trust Multi-Party Computation with Trusted Execution Environment. This is the joint work with Jiamin Sheng, Hongbin Wang, and Yichen Chang. We are with National University of Singapore. Jianting Ning is with Fujian Normal University and Chinese Academy of Sciences. Secure multi-party computation allows a set of parties to jointly compute a function on their sensitive inputs without revealing anything beyond the output of the function. It can be used in a wide range of privacy-preserving applications, including secure medical analysis on personal health issues and secure machine learning. A lot of previous works have been proposed to evaluate a function in MPC, such as coupled circuit and homomorphic encryption. However, they leave much to be desired because of the expensive overhead in communication and computation. Trusted execution environment such as Intel SGX offers a pragmatic solution to reduce these costs. It creates an isolated region in memory in the enclave. The adversary cannot access data in this region from untrusted operating system, hypervisor, and BIOS. Additionally, it provides some other functionalities, such as measurement, data setting for allowing data to be reloaded into the enclave before verifying integrity, and the remote testing allows the user to verify whether the code has been loaded into the enclave securely and correctly. With the help of trusted execution environment, one can design a much more efficient approach to realize secure multi-party computation. We can allow multiple parties to deliver their inputs to the enclave directly and evaluate the function over the plaintext. After the computation terminates, the enclave broadcasts the final outputs to all parties. However, TEEs may not be considered as a trusted third party because of the vulnerability to some side channel attacks. This is an architecture for an SGX application. Its enclave contains a user-defined application and some libraries. A series of attacks have been discovered against the user-defined application, especially when the developer is inexperienced. These attacks come from, for example, memory access pattern, control flow, and timing channel. However, some application libraries provided by the SGX SDK may have a higher confidence level. They typically undergo a rigorous security analysis and test in implementation, so they are less likely to be compromised by these side channel attacks. So, we mainly consider three levels of trust in TEE. Firstly, some people believe the application provided by the vendor is robust enough to prevent side channel attacks, so they can choose to completely trust the TEE for the sake of performance benefits in private computation. Secondly, some people would like to partially trust TEE that they accept some routines in the libraries can be kept confidential, while other parts of the application potentially might be leaked by the side channel attack. In this work, we consider a partial trust where a user trusts the implementation of secure channel and cryptography primitives in libraries. The user believes that the session key used in her communication with the enclave, as well as secret keys, would not be leaked via side channel in TEE execution. Lastly, consider that the data used is highly sensitive, and any leakage would lead to a critical interest risk. Some people do not trust TEE at all, including both user-defined application and application libraries. Motivated by a mixture of trusts perceived by different parties, we discussed a scenario of hybrid trust computing that some parties would like to trust TEE from others, while others might only have a partial trust in TEE or even does not trust it at all. Here we give an example involving three parties, a client and two TEE-enabled servers. The client holds a pair of parameters alpha1 and alpha2 as input, and each server has a large database. The function needed to be evaluated is divided into two phases. At the beginning, the client distributes the parameter to two servers, and they perform a function falpha1d1 and falpha2d2 in local. Taking these results as inputs, both servers evaluate another function g. Finally, they return partial output O1 and O2 to the client, and the client can combine them in local. In this setting, we assume that there are three levels of trust among these parties. Consider that the databases contain the utmost sensitive data, and any leakage would lead to a critical interest risk. Both servers do not trust TEE from each other. On the contrary, even though the parameter used is also sensitive, it induces These are consequences if compromised. So the client would like to have a higher trust in TEs of two servers. For those applications that are less likely to be compromised by side-channel attacks, the client completely trusts its TE. For the other, the client chooses to have a partial trust in its TE. We find that this computing paradigm can be instantiated to support a wide range of privacy-preserving applications. Here, we show one of its potential applications, and it is about the distributed query on banking statistics. The government queries for the total fiscal spending last year of different departments in two databases, D1 and D2, maintained by two banks. It can use a select and join SQL query like this one. In this application, neither bank wants to share its database for taking a great critical risk if any records leak. They do not want to use TE because they are not sure whether the other party can learn encrypt information from side-channel attack. So both of them prefer a secure two-party protocol with probable security guarantee. However, the government would like to use TE because the parameters it uses are not so sensitive as the databases from two banks. The government can completely or partially trust its bank's TE depending on the side-channel vulnerability analysis of its program executing a database query. Our goal is to propose a solution for realizing hybrid trust computing. So basically, we propose a generic framework for it. Based on that, we formalize the TE-like hardware and propose a select and join protocol in the distributed query setting as an instance. After that, we provide rigorous security analysis in the UC framework and evaluate the efficiency of our scheme in the real-world application. In this talk, I mainly introduce the generic framework and its instantiation in designing a select and join query protocol, as well as their experimental results. For the formalization and security analysis, they are a little bit theoretical, so please refer to our paper if you are interested in them. In this work, we propose a generic framework for the hybrid trust computing. The main idea to partition a function is based on the fact whether a party is willing to trust the TE from others. If the client would like to completely trust the TE in server, we can allow the function f to be performed inside the enclave. At the beginning, the client initializes a symmetric key k and delivers it to the enclave via a secure channel established by remote destination. Then, the client encrypts the parameter with k and submits the ciphertext. Next, the server decrypts alpha I inside the enclave and evaluates the function in plaintext. If the client would like to partially trust the TE in server, the function f is split into two parts. One is a keyed function f1 that relies on a secret key k, and the other is a function f2 without using a secret key. Initially, the client shares k with server's enclave. Then the server performs f1 in the enclave with help of k, and the client processes his input alpha I with k as well. Finally, they conduct a 2PC to evaluate f2 and get the result Ri. For the function g, because both servers do not trust the TE from each other, we have them engaging in a conventional cryptographic two-party computation. It can be implemented by three typical ways, including double circuit, secret sharing, and homomorphic encryption. In the end, each server is allowed to receive a part of final output OI and then returns it to the client. We instantiate our framework in a three-party setting that a client submits a select and join distributed query to two servers. Now we introduce the design details of our protocol. The select is one of the typical SQL operators for compacting the database by removing those records unsatisfying a given condition in where. We assume that each record is a key value pair, and the user wants to pick out those records whose key is identical to a given parameter alpha. The baseline method to implement the algorithm using TEE is to sequentially read each record into the enclave, label on those should be kicked out, and finally write back unlabeled records after re-encryption. However, this solution can negate the data distribution of unlabeled records. A system insider may observe whether a record is written back or not after reading to the enclave. It can further leak the sensitive parameter in where. If a user completely trusts the TEE, we can mitigate this leakage by randomly permuting the input dataset using mere-brain shuffle before feeding it into the select operator. The mere-brain shuffle is able to obfuscate the order of the input records. It can make the adversary have no idea about the input distribution against the condition alpha. This secure select algorithm only encores a linear complexity. If a user partially trusts the TEE, we need to protect alpha before passing it to the enclave because, according to our assumption, any input data will be leaked via side-channel attack. We can allow the user and the enclave to share a secret key of a pseudo-random function by establishing a secure channel. Then they perform pseudo-random function on their input locally. Next, the server shuffles the entire dataset and picks out the records whose pseudo-random function value is equal to the given alpha. Note that in this protocol, the user has to trust 4 types of secret keys inside the enclave, including ones used in pseudo-random function, secure channel, pseudo-random permutation, and data encryption. The last 2 keys are necessary in the mere-brain shuffle. For the join protocol, 2 servers are required to perform a secure two-party computation. At the beginning, for each record in the database 2, the server to randomly samples a string using a pseudo-random function, and then creates a Bloom filter with a set of functions, hash functions. Then the server 2 delivers the Bloom filter to server 1. Similarly, server 1 randomly samples a string for each record in the database 1 using the same pseudo-random function, and filters out those eligible records using the Bloom filter. After that, it encrypts values of all remaining records and sending all of them to server 2. Consider that the Bloom filter has some false positive. We have server 2 create a Google hashing table using the same set of hash functions as a Bloom filter, and search for each record in R individually. If found, the join record is written to the output set. When we put the select and join protocols together, we propose a secure select and join protocol. At the beginning, both servers perform the select in local when they receive the parameter from the client. After that, server randomly splits the intermediate results R1 into 2 parts. Next, we allow 2 servers engaging in the join protocol twice by dual execution. For the first time, the server 1 plays the role of receiver that obtains a partial output RC1. For the second time, we perform the protocol in an opposite direction that allows server 2 to receive a partial output RC2. In this way, we can break the tie between the output of select and the input of join. Neither of servers can learn the complete final output. Last, we show the performance of our scheme. We implemented the protocol on Ubuntu operating system with the help of OpenEnclave. All messages between the client and enclave are encrypted in ESGCN algorithm. The left figure shows the normalized running time of select protocol. We can find that the mere-brain shuffle dominates the performance. It accounts for more than 80% of total running time. From the right figure, we know that our select protocol in the complete trust version is about 21,000 times more efficient than the state-of-the-art crypto-based solution Tenet. The above table shows the performance comparison of our join protocol with 3 crypto-based private set intersection schemes. We find that our scheme achieves the lowest communication when the dataset size larger than the 18th power 4 of 2 and achieves the lowest computational overhead in all dataset size. We have also simulated the select and join query on a 20th power 4 of 2 sized dataset, and with a quarter of records being selected, we find that our scheme only encores about 167 seconds. It reduces more than 18,000 times overhead in the crypto-based schemes. Okay, that's all. Thank you so much.